everybody.
Good morning.
Yeah, all right. Let's get into it. So, the first assignment to do, I was reminded, I hadn't sent the link, but you should have, I'll get that in your email. If you don't, let me know, and just drop it there before you turn into a pumpkin tonight. Yes, you don't want to become a pumpkin. Right.
I'm so
I don't know if that reference
What?
means
What?
anything.
What?
But
Midnight.
you know what happened to Cinderella.
Oh, okay.
That's what happened at midnight. Your carriage will turn into a pumpkin and you won't be able to get anywhere.
Because you didn't turn into quantum optics over there.
That's exactly what happened. Right, okay. As I mentioned, the next assignment is a shorter assignment. It's one longish problem, and it'll be due in a week, okay? And Ivy has agreed to do the problem session tomorrow for that. I will not be here, but she will, and that's in the room next door at 1 o'clock, all right? Okay, so let's see where we're at. So what we're interested in talking about today is, and what we started to introduce last time, is the sources of non-classical light, in particular squeeze light. How does one create squeeze light in the lab? To do that, we're just revisiting the whole story of how electromagnetic fields are radiated or created from currents, and so fundamentally, we have the QED interaction between the current density and the vector potential. And in the multipole expansion, which we always make in optics, because we're always talking about situations where the wavelengths are big compared to the size of the dipoles, then we think about it as an interaction between the electric dipole density or the polarization, which, I know this is backwards, what I really meant to say is the other way. The current is in oscillation. Okay, so oscillating dipoles create a current. All right. Right, so this is like D dot E, as we've seen for a single dipole. This is for an ensemble, a continuum, a dipole density. And if under some approximation, the quantum fluctuations in the sources are negligible and we can treat the current classically, then what the time evolution operator is then just a displacement operator that is something that generates coherent states. And so one of the take-home messages is that classical currents generate classical light, in the sense, formally, that the time evolution operator associated with a classical current is a displacement operator in phase space by an amount that is equal to the complex amplitude associated with this classical solution to Maxwell's equations, okay? If we had a non-deterministic stochastically varying current, then we would have a statistical mixture of coherent states. And that's the general class of what we're calling classical light. So classical currents produce that's how we're defining classical light, okay? Is the thing that comes from classical currents. Yes?
So we're defining classical light as something that comes from classical current, and that just happens to exactly match what we've been calling classical light this whole time.
That's correct. I wouldn't say it just happens to,
yeah.
but yes.
Right.
But yes, it's just another way of saying the same thing, yes. We defined it as a statistical mixture of coherent states, and that is the thing that comes from any classical current distribution in quantum mechanics, if we treat the field quantum. have the state of the quantum state of the field is described by a coherent state or a statistical mixture thereof. All right, excellent. So if we want to have something, we need something that for which this description isn't going to hold anymore. And an important class of methods by which we try to create sources that radiate non-classical light is by a kind of scattering process, whereby we have some kind of strong pump field. Typically, we think about this as a laser, but we don't necessarily have to, which pumps some matter, and that matter re-radiates in a way that is no longer described this way, okay? And we want to then study the properties of this re-radiated or scattered light, okay? Right, so, typically it's the case that we can think about the response, as the dipole response to this pumping by this field in a perturbative way, okay? In a sort of power series in the strength of the electric field, okay? So the lowest order response is the linear response, but if we have a strong enough field, then these nonlinear corrections become important, okay? So this is basically, this perturbative expansion is valid because the binding strength of the charges, the electrons, the nucleus is so strong, that electric field is so strong compared to the field that we're imposing that it, to lowest order, we can think about it, Hooke's law, as a linear response. If we stretch it much farther, it stretches linearly, but the field has to be strong enough. So these terms are typically small, okay? You have to have the electric field high in order for these terms. So these are, the chi is, as you may remember, is called the susceptibility. How susceptible is the field to becoming polarized, and linear susceptibility is the dominant effect. Then you might have a nonlinear on top of that, okay? So linear optics, if we think about it from a quantum perspective, then the polarization, the dipole density is proportional to the field, and as we kind of showed, I kind of went through it quickly, that is effectively something which is a scattering process which takes a photon out of one mode and either rescatters it forward into the same mode or scatters it into another mode, as in a beam splitter or a lens or the like. And the effect of that, the transformation on the field modes is a linear transformation, where this is some unitary matrix, which is the same one that we would have classically. It's how the classical amplitudes are scattered into one another in, say, a diffraction grating or interferometer or any kind of linear optical transformation. And so what that does is kind of, if we have a linear optical transformation, as we studied in homework last semester, if we start with a coherent state and it goes through the linear optics, it stays a coherent state. And the amplitudes are transformed exactly as the classical amplitudes do. So a linear optical transformation takes classical light to classical light. You can't make non-classical light from a linear optical medium. You need to go beyond that. Now, as I mentioned as an aside, this is something that we didn't really appreciate back in the day when I, studied this, 30x, 40 years ago, God knows anymore. It still can be interesting if your input state is not classical light. If we start with non-classical light, somehow made some other way, and put it through a linear optical transformation, there's interesting features there that many people are studying these days as a way of, making fun and profit. All right. So now we want to say, okay, so if we want to go, if we start with classical light, if this pump field is, say, a laser, which is described by some coherent state, or some maybe has some line width, but whatever, it's basically a coherent state. And we want to generate non-classical light on the output here, we need to go beyond this, and we need to think about the nonlinear optics, okay? So we're gonna have just a little bit of a mini lecture on nonlinear optics today. But first we'll start with classical description, and then we'll think about the quantum description, okay? So let's think about classical nonlinear optics. Okay, so let's suppose we have our field in that we're sending in, whatever the pump fields are. There's some electric field that, let's just say to start, is some linear combination of more than one frequency, okay? So let's say that I have, say this is the real part of some E that has some, say, two frequencies, for example. Let's just say there were two frequencies that were present with some complex amplitudes associated with them, okay? Let's suppose we had that. I'm gonna, for the moment, we'll come back, ignore the vector nature of the field. It's just too many hats and doodads to keep track of. We'll just, for the moment, just think about it in some polarization direction, okay? So if I have linear optics, then the polarization density is going to be, generally, I have to worry about the susceptibility is a function of the frequency. The response of the dipole depends on the frequency of the drive. But that's sort of not a hugely important point, but I'll put it in there just for the moment. So that's the induced dipole density that will radiate, okay? And that tells me, if I have linear optics, that the radiated field has the same frequency components as the input field. I can't make new frequency components with linear optics, okay? So the frequency components are unchanged. There are these two frequencies in the input field, and there are these two frequencies in the output field. The amount in those frequencies can change depending on how big the susceptibility is at those 2 points in the strength of the fields. But essentially, I can't change the spectrum. Okay, I can't change the spectrum by linear optics. I can move frequency components around into turns in different modes, but I can't change the frequency components.
Is that supposed to be tied to?
No, it's not. But it's omega 2, so there's a 2 in there, and I already got confused. Thank you. Yeah.
So the frequency as a whole can still change, it's just the fundamental, like, components of the signal? Like,
I can't, if the spectrum, I can't create new frequency components. If I start with, a certain spectrum, I can move I can re-radiate in different, but I can't create new frequency components. Because they happen, because the dipoles are oscillating at the same frequency as the drive. Okay, and you radiate at the frequency that you're oscillating. Okay. But if I think about, let's think about chi2 response. So that, I'll call it P2 here is going to be related to the square of those guys, right? And so what I'm going to have, if I have the same electric field, let's just say with these two frequency components, then I'm going to have the following kinds of terms. I'm going to have the real part of, say, chi2 at 2 omega 1. I'll just call it E1 here, squared e to the minus 2I, because there's going to be a term that looks like that when I square it. There's going to be a term that looks like that. There's going to be a term that looks like that, right? But remember, when I'm squaring the field, this field here is 1/2 E tilde plus E tilde star, right? That's the electric field, and then I square it. So there are going to be also terms that look like this. Plus complex conjugate. Okay. Everyone see that? Because when I take, if I write this and then I add to its complex conjugate and I square it, I'm going to get terms, the cross terms that look like this. Okay. So, well, I've already had the complex, that's the real part of all of that. This term we might call the beat note. It's the beat note between if you add two waves together and you look at the square, you're going to get the beat note between them, and it will oscillate at the difference frequency. Okay? So all of these terms exist, and what that says is that I'm going to, in principle, depending upon how the wave equation is solved, I could have light that is being radiated at twice the frequency of one of the waves or the other. I could also have something that oscillates at the sum frequency of the two waves, and I can have things that oscillate at the difference frequency of the two waves if I put in these two waves. And so what this process by which I start with, what I can think about this as two waves, and I can radiate a third wave coming out at a different frequency. And that process is known as three-wave mixing. There are three waves that are mixing together in this nonlinear response. Okay? Yes?
Those chi of 2 omega 1 to omega 2, those come after Fourier transformation.
Yeah, all of this, again, I kind of go back and forth. I can think about this as doing a Fourier transform, or I can think about it as what is the amplitude associated with specific frequency components. It's the same thing. Let's be more formal about it. We'll see how it goes. So what we want to understand is the process by which this source of oscillating current, which is oscillating at these different frequencies, radiates electromagnetic waves. Okay? To do that, we use Maxwell's equations. Okay? So if I wanted to think about this from the point of view of Maxwell's equations, I have the wave equation. The wave equation, which comes from Maxwell's equation, we all remember. If I look at it, I have the D'Alembert of the field, and that is equal to the source, which is the current. The derivative of the current is the oscillating field, is the accelerating, if you remember, accelerating charges. Current is proportional to velocity, the derivative of the velocity is accelerating charges radiate, right? So it's the derivative of the current that is the source, comes from Maxwell's equations, you can derive that all. And at the end of the day, because the current is the derivative of polarization, what you end up is the following. In my crazy set of units. Okay, so very good. All right, so this is the wave equation with a source, and if I'm going to break up this P, well, let's write this as Omar was suggesting in the frequency domain. So let's take the Fourier transform of this and write this like this. So that's just the Fourier transform of this equation, where every d by dt is replaced by a minus I omega. Okay, and that's how that comes, all right? So the minus I omega squared becomes minus omega squared.
Just making sure that, should that be a Laplace, not a gradient?
It should. Thank you, sorry. This, of course, is the Helmholtz equation with this, right? So now I'm going to break this up. I'm going to write this as the linear term plus, I'll call this P nonlinear, whatever the nonlinear piece is. It could have a chi2, it could have a chi3, etc. Okay? So let's plug all that back in together, and what that tells me is the following, that this equation can be written in the following form. Del squared plus k squared E is equal to minus omega squared over c squared times 4 pi p nonlinear, where I've defined k as omega squared over c squared times the index of refraction squared. I'll just write it this way, omega over c times the index of refraction, where the index of refraction is 1 plus 4 pi, the square root of 1 plus 4 pi, pi 1. So the linear susceptibility gives rise to the index of refraction, if we remember that. So this is the wave equation. If I didn't have any nonlinear term, this would just describe linear optics of light propagating through material that has some linear index of refraction. Okay, so now I want to look at the case of three-wave mixing. And for that purpose, I'm going to look at the specific example of some frequency generation. Okay, so I'm going to be very fancy here. I got color. So I have a Chi2 crystal, a crystal that has a reasonably big nonlinear response, and I'm going to put in two laser beams, one at this frequency, omega 1, and one at this frequency, omega 2, with two different colors. And the sum frequency of them is going to generate a wave that oscillates at the sum frequency. And I want to study what is the electric field that's radiated by the current that is oscillating at the sum frequency. Okay, so these other beams will pass through as well, and they don't stop here. I'm drawing what is also emerging in addition. Yeah.
Where is the current that is oscillating at the sum frequency?
The current is inside the crystal. So you're driving the crystal, you're pulling the electrons away from that, you're creating a dipole density, but importantly, that dipole density that's oscillating. So this is my, remember the current is the derivative of the polarization. That oscillating polarization is oscillating at these various frequencies. So I'm looking at the current that is this source. Okay, does that make sense?
Yeah.
So let's write this down. So I'm looking at this equation at frequency. I want to know what is the electric field that is radiated at this frequency. And that's coming from this source here. Okay. So that source over there, that's my P, so I have to put that into the equation, and that's equal to minus omega 3 squared over c cubed 4 pi, and then I have chi 2 at this frequency, and then I have the electric field of wave 1 and the electric field of wave 2 star. No, it's not star, because this is a sum frequency. Excuse me, we'll come to the difference frequency in a moment. Times this. I've already put this in the frequency domain, so those frequencies cancel. Omega 1 plus omega 2 equals omega 3. So the time dependence on both of these sides canceled, because this oscillated like the sum of those two. Is that clear? Yep.
Should that be omega subscript 3 squared, not omega cubed? After the sign first time.
Omega 3 squared, yes. 3's, 2's, subscripts, yep. Right. All right, so we want to solve this equation. So the way we often do it, and that's appropriate here, is to, first of all, let's call, this is all collinear. These two beams are along the same direction. And so the beam that's radiated will be along the same direction. This is a collinear configuration. And we're going to thus write this, it only varies along, any one of these waves only varies along the z direction. And that z direction is gonna have some amplitude that varies as a function of the distance along the crystal, which I'm calling the z direction. If there was no change in the amplitude, it would just be a plane wave, that's what I'm putting in. And the way in which the amplitude changes as a function of time is defined by this amplitude, okay? So that's just an ansatz I'm making, that this is a plane wave in that direction with some amplitude that changes as a function of z as the field is radiated, okay? Now, the next thing we do is make what's known as the slowly varying envelope approximation. SVEA, slowly varying envelope approximation, which is, this is the envelope of the waves, if I thought about it as a pulse. And because we have optical fields and the rate of change of this is slow because we've already made the perturbative approximation, what we're saying is that the rate of change of this amplitude as a function of distance propagated is much, much less than the wavelength, right? This is equal to 2 pi e over lambda. So it's changing much more slowly than the wavelength is oscillating, okay? And that equivalently is saying that the second derivative is much, much less than k times the first derivative. Okay. That's the slowly varying envelope approximation. Yeah?
Even though this is classical, is it the same math as like the WKB approximation?
Yeah, I mean, it's just, I mean, that occurs also in the WKB approximation if I have, you know, I think about the situation where I have a potential and the way the potential varies compared to the Broglie wavelength. It's a similar math for different reasons.
Got it, got it.
All right, so with that, then for any frequency is equal to the second, only depends on the z-axis. So this is equal to, if I look at the second derivative of this, second derivative of the thing that's in here, then what I'm going to find is that's equal to the following. It's equal to minus k squared plus 2ik d z plus the second derivative of this plus k squared e to the I k. So that comes from just taking the second derivative. You can kind of see how all those terms come out, because there's going to be a second derivative of this, a second derivative of this, and then the cross terms. Okay, just do the derivative, that's what you get. So this cancels this. And then this is small compared to this under the slowly varying envelope approximation. Okay, so putting that together over here in this equation, what we see that this equation then becomes 2ik3 times the derivative of E3 with respect to z, e to the ik3 z, is equal to minus omega 3 squared over c squared 4 pi chi 2 at omega 3 times e1 tilde e2 tilde e to the ik1 plus k2 z. Yeah.
Why is there tilde over the envelope on the left side of the equation?
Why are all these guys have tildes?
Yeah, why that one specifically?
They all should have tildes because,
Oh.
they all should have tildes, because I'm in the Fourier domain. Yeah, I'm sorry, I'm being not very precise. So, putting this all together, what this tells me is that the amount of electric field radiated by the source as a function of the distance propagated in the crystal satisfies the following differential equation. It is I omega 3 over n3c times 2 pi chi 2 at omega 3 E1 tilde E2 tilde e to the I e to minus I delta k z, where delta k is equal to k3 minus k1 plus k2. Once I divide that on the other side. Everyone see that? Right? So this is equal to omega 3 over c n3 minus omega 1 over c n1 minus omega 2 over c n2. Because remember, k is omega over c times the index of refraction, okay? Remember, we've also set omega 3 to be equal, we've chosen this. Now, you might say, why is delta k not 0? Because we said this was true. And the reason is that the index of refraction is generally a function of frequency. So that these guys don't necessarily are not all the same. If n1 was equal to n2 was equal to n3, then I would satisfy this automatically. But generally that's not the case. We'll come back to that in a moment. This is something that's known as phase matching. We'll come back to that in a moment. Okay? So, all right, let's look at this problem again. Here's our problem. We send them these two pump waves, one at omega 1, one at omega 2, and they're coming into this crystal. And we're going to generate some blue light. This is how you do it in the lab. You know, you don't get every color from the manufacturers. You have to mix and match like, you know, Play-Doh that you used to do. Yeah?
Yeah, I have a question from here. So here we have all of these new frequency components at the same time, or
They're all there. They're all there. And they all, in principle, can radiate. Whether they will or not, as we're going to see in a moment, depends on the phase matching condition. Okay? Right now I'm looking, so in principle, I could also generate light at the double omega 1 and light at double omega 2, because both of those, I put both of those, I could double, it will also in principle double omega 1 and double omega 2, but the degree, the efficiency which it does that, we'll see in a moment.
And
Yes?
Is that the reason why delta K is not 0, that we have these other frequencies?
The reason that delta K is not 0 is that this condition, if delta K is 0, that implies that omega 3 times n3 is equal to omega 1 times n1 plus omega 2 times n2. But that's impossible in general, because generally these things are functions of frequency in a way that if this is satisfied, this won't be satisfied. Now we'll come back to that. There's a trick we can play in a moment to make it 0, but I'm going to come back to that. Yeah?
Another question. So here we cannot use rotating blade approximation to get rid of those fast oscillating frequencies.
No, I mean, in some sense, we already did. I mean, I guess I'm trying to, the fields, I mean, at the end of the day, the picture is the following. I think about this, if I just think about this classically, I have a charge bound by a spring to let's say, the nucleus, okay? And then I come in with a force that is oscillating at some frequency. What it will do is cause those charges to go up and down at that frequency, and those charges that go up and down that frequency will radiate that frequency. If I have this nonlinear process, the beat notes between them can also drive this. So these are the terms that are existing. There's no fast things that are to be neglected. These are the things that radiate. All right, so if these are strong, intense laser fields, the process by which I drive this and the amount of current that I get in this is going to be small, because generally chi2 is not a very big thing. So the amount of power that I radiate is going to be tiny compared to the power that goes in. And if that's the case, then we can make what's called the non-depleted pump approximation, okay? Which is basically to say that these electric fields are constant as a function of Z. So I'm not actually depleting. I mean, it's true, there's going to be some amount of the energy that is, if I'm generating energy in wave 3, it had to have come from the energy in waves 1 and 2. But if this is a very small amount of energy, I can neglect that. Okay? Yeah.
So if we're not depleting the pump, then that means even after we leave the crystal, the signal
Is about the same.
is still the same.
Is about the same.
So that
It's not exactly the same, it's about the same.
But we're only considering the part that's being generated by the beat note here.
There's well, it's the sum frequency, it's not the beat note. The beat note's the difference. But yes, we're assuming that there is going to be some amount of current that's oscillating at the sum frequency. It will radiate. But the amount of energy that it's radiating is going to be tiny compared to the amount of energy I put in. So to some good approximation, I treat these as constants. So then I can just integrate the equation, okay? And so now I just integrate it, and the integral of this, it says that the amplitude as a function of C is going to be equal to I omega 3 over N3 C 2 pi chi 2 and then I get e to the minus I delta kz minus 1 over minus I delta kz. That's just the integral over this from 0 to z. That's the integral, okay? Which is equal to e to the minus I delta k z over 2 times the not the sinc function delta k z over 2 times z over 2, where the sinc function is sine x over x. Okay? Right. So this tells me that the intensity, I'll just say the square of the amplitude at the, if the crystal has a length L, so at the output face, the amount of intensity, or the square of the amplitude, is proportional to the product of the intensities at the input phase, assuming non-depleted waves, times the sinh squared of delta KL over L times K times L squared over 4. Okay. So I get this quadratic growth, except there's a phase mismatch question, the question of delta K, right? What does the sinc function look like? Everyone remember? Kind of looks like this.
What's the max of this one?
1. Because L'Hopital. X goes to 0, this is 1. And it then falls off with K, X is pi. Okay? So unless delta K is close to 0, the delta KL is small compared to pi, I'm not going to get much out. The phase mismatch is going to make this not an efficient process. Now, why do we call this phase matching? Well, so let's just think about what's happening in this crystal. What's happening in this crystal is that I have this wave, these two waves that add together and generate a polarization current, which is propagating. So I have this polarization current that's coming from the sum of these two waves. That is to say, this thing is equal to chi 2 E1, E2. And this thing is generating a polarization wave that's propagating like this, okay? Now, what we said is we're looking at how this thing radiates. This thing oscillates at the frequency omega 3. Now, the wave that it's radiating has the same frequency, but not necessarily the same wavelength because of the index of refraction. So the phase velocity of this is omega 3 over K3, which is equal to the index of refraction, C over the index of refraction. That's the phase velocity, right? Okay. We can remember all that stuff. But the velocity at which the polarization wave is moving is not necessarily the same because of the fact that there's a phase mismatch, right? This is going to go at this thing. And this ratio is not necessarily the same as that ratio, okay? Because of the fact that we just described before. What that means is that these waves will get out of phase with one another. The radiating wave, the current that is moving along this crystal, will get out of phase with the wave that it's radiating and make this an inefficient process. You need to have these two waves be phase matched. They need to move with the same phase velocity in order for this to be an efficient process, okay? So how can we do that? There's a little bit of a trick to the trade here. So let me come back to this board. And this, I'm gonna now come back and put in the polarizations. So let's say these guys were both linearly polarized, and let's put them linearly polarized in the same direction. But this wave need not be radiated with the same polarization if the crystal is birefringent, meaning that its index of refraction depends on the polarization. It's a crystal that stretches differently whether it's being pulled in this direction or that direction. And so if it's birefringent, I can look at the wave that is, say, polarized in another direction. We can think about these as the eigenvectors of the index of refraction, and the two directions are historically called ordinary and extraordinary polarization. So we can say, these guys are the ordinary and these guys are the extraordinary. Why the heck it was called that, I don't know. Okay, but the point here then is the following. So if I choose this in such a way, or maybe I'll come back to this board over here. So this is what's known as type 1 phase matching. This is a bunch of jargon, but those of you who are in the lab hear this. So what the heck does this mean? Type 1 phase matching is that the omega 1 and omega 2 in the same polarization, and omega 3 in orthogonal. Then it is possible for me to simultaneously satisfy this equation and this equation. By orienting the optical axis of the crystal such that this index of refraction is equal to this ratio. I can always find a orientation of the crystal such this is true. Okay? Yeah?
How can we make sure that omega 3 is orthogonal?
We don't, it's not that omega 3 is orthogonal. We choose the orientation of the crystal such that this is true. Okay, so we choose the orientation of the crystal such that the index of refraction for a wave which is polarized in this direction, omega 3, satisfies this equation. So once I do this, I've chosen the orientation of the crystal such that this is true. I need to know the dispersive relations. How does the index of refraction change as a function of frequency? If I orientate the crystal as true, then delta K will be 0. And when delta K is 0, then, coming back over here, I get the maximum conversion. So I've oriented the crystal in such a way that this is the efficient wave that will radiate. The wave which is polarized with omega in the other direction will not be phase matched. And thus, if it's not phase matched, the sink is effectively 0 and it won't radiate. It only radiates when the phase matching, if the phase matching condition is met. Yes, Ari.
Do you also have to make sure the crystal's like the perfect length so that it rotates into the X-ray axis?
It's not that it's rotating into that, it's that it is radiating into that. So the point is the following. I am pushing on the wave the crystal this way, but the dipoles oscillate that way. Why do they do that? Because the crystal is birefringent. Its polarizability is not scalar. You push it this way, but it responds that way. And when it's oscillating in that way, it's in phase, the oscillating current is in phase and it will radiate the most efficiently. So that current, which is being pushed in that direction, is the one that's phase matched. Very good. All right. So that's some frequency generation, and if I chose it with omega 1 equals omega 2, it's called frequency doubling. And we do it all the time. That's how you make blue light when you only have infrared around. You use a doubling crystal to do it. All right. So now I want to talk about a slightly different process that is one that we kind of mentioned up ahead, which is known as parametric amplification. Now, parametric amplification, you just studied, or you're about to hand in your homework, so I hope you study it. When we talk about a parametric oscillator as a mechanical process. But now we're going to think about it from the point of view of the electromagnetic waves. It's the same thing, but here's the process. So let's imagine the following thing. So now I'm going to do something slightly differently. Instead of putting in the red and the orange waves, I'm going to send in the blue and say the red. Okay? So let's say that I send in a blue wave and I send in also, so this is going to be a strong pump, very intense pump. And now I'm going to also send in this case, a weak signal. Okay? So this is my pump, and this is my signal. And this is my Chi2 crystal. Okay? What is going to happen is so there's these two waves here. In this case, I have K1 propagating along this direction, and I have K2, which is propagating along this direction. If I phase match, there will be a third wave radiated. Let me call this K pump and this K signal. There's going to be a third wave radiated if it's phase matched. That third wave, for historical reasons that I don't know, is called the idler. It idles. I don't know why it's called the idler, but it's called the idler. Okay? So there will be a third wave. This is another example of three-wave mixing. This three-wave mixing is related to the beat note. So in this case, the idler frequency is equal to the pump minus the signal. Okay? So that's to say the pump, I give up on color. Just before, so this is the difference frequency that we discussed this moment, which is one of the things that can be radiated. Similarly, what we want for phase matching is we want that the pump, that these two things add up. So this is the phase matching condition. And we can do this again using birefringence. And in type 1 phase matching, these two have the same polarization, and this one has the orbital. Type 2 phase matching is when one of these is ordinary and the other one is extraordinary. We could do that too. Okay. All right, so now what I want to do is write down the equations of motion, just as we did before, but now for difference frequency. Okay? So what I will find in this case is that it's similar, basically the same equations, but obviously they're slightly different. So I have I 2 pi omega signal over the index refraction of the signal times C times chi 2 at the signal. And then I have, in this case, the pump remember, so this thing had an oscillation that was either the minus I pump minus idler, whereas this guy oscillated like that. So the beat note here, which is the difference between the pump and the idler, is oscillating at the frequency of the signal. Is that clear? Okay, so these guys are equal. I'm just going to put it away. And similarly, I'm going to have because this thing oscillated at the difference frequency between the pump and the signal, and that difference frequency is the idler. And then there's the third equation for the pump. Which is the sum frequency. Okay? So now, again, if my pump is extremely strong, I can make the non-depleted pump approximation. So the non-depleted pump approximation basically says that this is 0. It's basically the pump is not depleted, it's constant along that. I can treat it as a constant. So this equation is, and this is a constant. So let's look at those equations. What I then have is the following. Let's take, to start, we'll come back, let's look at collinear phase matching. So I'm going to just take these guys to be along the same direction, everything along the same z axis, so that I have this kind of phase matching. Okay, so let's just assume for the moment, I'll come back to the case where they weren't collinear in a second. Let's write down the equations of motion. What we have is that the rate of change of the signal amplitude as a function of the distance propagated is some constant, I'll call it kappa sub s times e idler tilde star. And the rate of change of the idler amplitude is some constant, I'll call kappa sub I times the signal star, where I'm calling this constant kappa sub s and this constant kappa sub I. These equations might look kind of familiar. So we have here these two modes that are coupled together in a coupled set of ODEs. How do you solve that equation, those differential equations? Take another derivative, right? So if I take the second derivative of this equation, I get that, and then I can, this is the C, which is equal to kappa S kappa I star. Okay, so that's, everyone see that? This is a real number, because I multiply that by its complex conjugate, gets rid of the i's, everything. So this, I'll call this kappa squared. Or kappa squared here is 2 pi, one of these guys was wrong anyway, this should be the I there. Squared, omega signal, omega Eigler over n signal, n Eigler c squared, chi 2 squared times the intensity of the pump. Right? So I have now the differential equation, the second derivative of this amplitude minus kappa squared, where kappa is a real number, kappa squared is a real number, is equal to 0. And the similar thing is true for the Eigler. Okay, what's the solution to that differential equation? I could write it in terms of exponentials, or I can write it in terms of hyperbolic sines and cosines. It's hyperbolic because it's a minus sign here, right? If this is plus, this would be the simple harmonic oscillator with sines and cosines, or e to the plus or minus i's in this case. So I can write the solution here as the amplitude function of this. There are two initial conditions I need for a second order differential equation. I need to know what the initial amplitude and its initial derivative is. And similarly for the Eigler. Okay? And so the solution to this equation this derivative over here is equal to and similarly, okay? So, do you recognize those solutions? One of these guys is a star.
Reminds me of squeezing.
It does. This is a Bogoliubov transformation. The amplitude at the output is related to the amplitude of the input and something related to the complex conjugate. This is like a two-mode. The one you're studying in problem 2 of your homework, right? It's exactly the same thing. The A dagger in some mode out is the Kosh. What are the others? Who wrote this stuff? God, what kind of nonsense is this? This is the Kosh. This is the Kosh. And this is the cinch. Oh. Okay. Jesus. Get out of bed today. Now it's right.
Now it looks like.
No, it's okay. Yeah, no wonder you don't know what that is. Okay, so interesting. Come back to this in a moment. Now, in our situation, when we have this, we have actually the input field in the either was 0. So this term is not there, and this term is not there. Okay. So the solution to this classical equation is twofold. Firstly, we have amplification. We amplify the signal. Remember, when kappa z gets big, this looks like something that goes like an exponential rise with an amplification rate depends on kappa. And that kappa is proportional to the field amplitude. This is parametric amplification of exactly the type that we studied in problem 1 mechanically. We are parametrically amplifying the signal the same way that you do when you swing your legs on the swing in the third, and you amplify the signal. This is parametric amplification. At the same time, in this context, we also generate this additional beam in the three-way mixing process, the idler beam. And the idler beam is proportional to the complex conjugate of the signal. So this is sometimes known as phase conjugation. Right. Okay. So that's how this process of parametric amplification is a three-way mixing process. Okay. Now we got a hint of this, how this is closely related to squeezing. I'll just do one quick preview and we'll finish this up next time. What's the quantum description of this process? Yeah.
You replace the modes with the quadratures associated with A plus or A minus.
Yes, well, exactly. So that's exactly right. So let's go back to what we had at the beginning of the lecture. We had the interaction Hamiltonian. My interaction Hamiltonian, if I don't make any classical approximation, is this. Okay. Now, this, in our case, is going to be chi2 times the product of the electric fields. Okay. So if I have multiple modes in the system, my electric field might be something times, if I look at the positive frequency component of this, it's going to have a part that's related to, say, the pump, and something that's related to the signal, and something related to the idler. For those three modes that are participating, that are strongly coupled together in the phase matching, because they're phase matching. And so this Hamiltonian is gonna have some terms in it that look like the following. This has the frequency e to the minus I omega p minus sigma plus Eifler. Because this thing oscillates like e to the minus I omega t, e to the plus signal. And then I'm gonna have a term that looks like the opposite. There's gonna be terms in the Hamiltonian that look like this. They are the terms that are related to the beating between the pump and the signal leading to the idler, and vice versa, the beating of the pump with the idler leading to the signal. The thing to see here is that the three-wave mixing process involves, from the quantum perspective, from the perspective of the quanta, involves how photons are being created and annihilated in the different modes. So in this case, this is a process by which a pump photon is annihilated, and the signal and idler are created. So I sent into this photon, but through the three-way mixing process, I have these two photons. I annihilate a pump and create a signal and an idler. The three-way mixing has that as one of the things that can happen, and it will be dominant when that's phase matched, for exactly the reasons before. Now, in the problem of parametric amplification, what we have is stimulated emission, because we're sending in some signal, right? And so this is a kind of stimulated emission into that, at the same time that I generate the pump wave. We're gonna come back to this, even if I don't put in a signal, this will happen. That's known as spontaneous parametric amplification. Yeah?
If it happens spontaneously when you just put in pump, wouldn't it happen with every set
It
of
does,
Okay.
but only the ones that are phase matched. So the ones that aren't phase matched, we need to satisfy these two conditions. The condition that omega 3 is equal to omega 1 plus omega 2, and that K3 is equal to K1 plus K2.
But every pair of signal idler
That
could
satisfies these conditions happens. With a amplitude that depends on how good the phase matching was. Yeah?
So is it equivalent to saying that these are the energy conservation?
Exactly.
momentum?
So it's basically saying that energy must be conserved and momentum is conserved.
And then I have three available modes, and it's like that general three available mode scattering.
That's right. So I just want to conclude though so we'll come back to the whole story of parametric down. This, by the way, is sometimes known as down conversion. Because I down converted the light from a high frequency to a lower frequency. That's why it's called down conversion. So it's sometimes known as parametric down conversion, and it's spontaneous parametric down conversion, okay? Which happens in a three-way, but also can happen in a four-way mixing process. But I just want to conclude with one last thing. Suppose I had the non-depleted pump approximation. So I send in this pump, it's in a strong coherent state. In that case, when I make the strong depleted pump approximation, I can replace the quantum operator by just the constant. Okay? Now, I want you to look at that Hamiltonian. Does it look like something that you're just doing for homework?
Yes.
Yes. This is two-mode squeezing. So that's how you make two-mode squeeze states, is through spontaneous parametric down conversion. In that case, you're not putting in any signal, you make squeeze vacuum. Because you would not have any input signal either, and it would spontaneously produce. Now, if you have the degenerate case, if your signal mode equals, so I have my pump, and I've set it up such that there is a case where they're both the same, the signal and the either are the same frequency, which add up to the pump, then it's one mode squeezing. So the way that one creates squeeze light is through spontaneous parametric down conversion. And it's intimately related as we remember the squeeze states when looked at in the Fock basis are superpositions of even numbers of photons. And the reason is that the process that creates squeezing is through pair creation. You're creating pairs of photons through this process of spontaneous parametric down conversion.
And thus, they could be entangled as well.
We'll come back to that. Yeah, we'll talk about the entanglement as well. It's another feature of this. All right. We'll finish this up next week. Just gonna say a few more words about it, but you get the essence. Have a good afternoon.
Is there a Hamiltonian?
Hamiltonian is permission.